Okay, anybody viewing this, we're taking a little bit of time to do number 34 on 773, page 407, bottom right, because it's a rather tough problem. It's weird because it isn't like examples. We're going to do number 34 and that's demonstrate those two, and then we will on the quiz review. So it's part of the review, I guess. Page 407 at the bottom, it says, we're supposed to do 4 different things. And the instructions are above number 33 that go with 34 as well. And it says, use cylindrical shells, which is the bundt cake method, to find the volume of the solid generated by revolving the shaded region about the indicated axis. So number 34, it's actually 4 problems in one dealing with the same shape. And the first one that they want us to do is to revolve that thing around the x-axis and find the volume after doing that. And that'll be a very strange looking thing. It'll have a parabolic interior and kind of a strange bumpy little exterior that'll sit on a ridge on the outside. Anyway, we're going to spin it around the x-axis. But if you'll notice, before we do that, each of the equations is written x equals something in terms of y. Both of them are written that way. A good indication that we want to actually integrate along the y-axis because it's written in terms of y. So, and I'm not really great at drawing this. We'll see how this works out. So I can point to things. Kind of goes like this. And then it comes out like that. And that is a really horrible drawing. And this point right here is the point 2, 2 where they cross, which means that this over here where they cross is 2. And that shouldn't have gone up above it. It should have joined it just like that. This is the number 2, and it starts at 0, this other cross point, and so we are going to integrate from 0 to 2, and our slices are going to be, this is a representative slice right here, our slices are going to be like this, because we're integrating along the y, and we're collecting slices from here to here. And since we're spinning it around the x, our slices are parallel to the axis of rotation, which is why they told you to use the shell method. You following me? So if I take this slice, now it's kind of hard to imagine because we're on a 2-dimension here, but what I'm doing is I'm taking this slice where my marker is, and I'm going either back behind the board or pulling it forward like this, however you see it. If I pull it forward like this and make a circle and then go back behind the board and come back up and join it here, that's what I've got, kind of thing. You follow? Do you see what's happening? And so since I'm using the shell method, and I told you I required this sort of a drawing, since this is laying flat, I'm going to draw my skinny little box. I'm going to draw it flat too, so that it matches and it's a little easier to see. And it goes out like this. And that right there is that ring laid out flat like this. Got it? You see what's happening? Okay. And so this right here is going to be how wide? dy. It's just to remind us we're going along the y. Everything we put in our integral is going to be a y value.
Taking pictures.
For those of you just joining us, we're doing number 34 at the bottom of page 407. Seems to cause some people some problems. So if you haven't gotten there yet, you might want to look. Okay, it's going to be dy because we're integrating along the y, and so everything in my integral is going to have a y in it. So this is dy this time. What is this right here from here to here?
The back curve minus the other curve.
What was this one up here? X equals what?
Y
Y to the 4th over 4?
Yeah. Minus
Minus what?
y squared over 2.
Is that okay if I write it like that?
Yeah.
Okay, so you can clearly see the coefficients. That little piece right here, this part right here, that is this. And that is this function minus this one. Isn't it? So this right here is going to be 1/2 y squared minus 1/4 y squared, or y to the 4th minus 1/2 y squared. That's that length right there. It is this minus this at this particular y value. Does that make good sense to you or not? Okay. And what is this? the circumference of this thing that we wrap around like this, and its radius goes from here to here. How far is it to here? Y. That's how far it is to that slice, Y. And so the circumference of that particular slice is 2 pi Y. Y'all see that or not really? You good? Yeah? I thought you were raising your hand. Okay, all right. So the integral then is going to be to collect all of these slabs. And the volume of each of those slabs is 2 pi y times 1/2 y, this is supposed to be y squared. 1/2 y squared minus all of 1/4 y to the 4th minus 1/2 y squared dy. And at that point, you can grab your calculator, or you can simplify in there a little bit. This is going to be minus right there, and I've got 1/2 y squared plus 1/2 y squared. So I could simplify that a bit as y times y squared minus 1/4 y to the 4th dy. And if you had to do this by hand, you could distribute that y, which would be y cubed minus 1/4 y to the 5th dy. And you could integrate those because that's just a polynomial. Don't forget your 2 pi. Oh, and by the way, what are we integrating from and to?
0 to 2.
Yeah, 0 to 2. That's the collection of the slabs, 0 to 2. So if you simplified this mess a little bit, you could get it down to there, and you could do it by hand if you had to. Or you can do it with your calculator, and that's still going to be easier and have less opportunity for errors. So it might be wise to do a little algebraic simplifying before you actually plug something in. But you could do it from here if you're real careful and have your parentheses organized. I'm not actually going to do that because the integral now, that's something you should be familiar with. It should be 8 pi thirds when you're done. So I'll just write that down here. What we're supposed to get is 8 pi thirds. Now you may get a decimal if you use your calculator for this. Divide it by pi and see if you get 8 thirds, which would be 2.6 repeated. Okay, that's just A. Now I'm going to show you B and give you a little bit of an idea, and then you're going to do the others on yourself, the C and D. Would you rather me do a C or a D, or do you want me to do the B? Because they all have the same change in concept. All three of them do that I'm about to show you in B. You want to just see B?
Sure.
Okay. So in B it says, now we're not going to rotate it about the line y equals x. We're going to rotate it about the line y equals 2. So we are going to take this line right here. I'll put a different color on because I've got quite a mess going already. Okay. We're going to rotate these same slices, but we're going to rotate them about this line right here. It's going to go around this way. And the only thing that's going to change, folks, in that slab is its radius. What's the radius of this particular wraparound going to be?
2 minus y.
Yeah, 2 minus y, because this thing's still located at y. It's up to 2 here, and so if this is y from here to here, then from here to here is 2 minus y. Does that make sense? Or not?
Could you review how that's the radius? Like how you take that slab and lay it out real quick?
Thank you for coming late.
My bad.
This is the slab, okay? Now, I got to go back to the A part where we're rotating it about this line. Okay? We take that thing and we pull it out of the board like this in a circle, and we come down to here, and then we go back behind the board and finish the circle coming up so that I have something like this. And then I lay that out like this, and that's what I've got here.
Okay.
And so if I take the front of that, I've cut it. I've cut the ring that I had like this, and I've laid it out. That means that this distance right here is still this distance.
Okay.
Does that make sense? Yeah?
Yeah.
Okay. And that distance is, because we're integrating along the y, is the right one minus the left one. That's what I have here.
Okay.
You following? This is dy thick because I'm integrating from here to here, which is along the y. So this is dy, not dx. And this thing, this back thing right here, is the circumference of my, and that circumference is dependent upon a radius. So you got to ask yourself, if you visualize this thing going around like this, the radius is from here to here. And that slab is y up. That's where it's located, is at y. So the circumference of that thing is 2 pi r or 2 pi y.
Okay, but now we're going.
Yes, now we're going around this line this way, which means this is the radius that I seek. And that is no longer y. This is still y. This is 2 minus 1.
Okay.
Does that make sense?
Have a pi though in this one.
Huh?
Like where did the, I know that there's a certain reason, but like in the first one, we go around the x, it's 2 pi y, and then it's just 2 minus y. Where the,
Well, that's-
like what?
The y gets replaced with 2 minus y, not the whole thing. It's still 2 pi
Oh,
times the radius, which is
2 minus y.
2 minus y.
Okay, that makes sense. Yep.
That's all that changes.
Yeah, okay.
Okay, and so this right here is going to change to 2 minus y. That's the only thing that's going to change. We're still collecting slices from 0 to 2. So this doesn't change. And the volume of this is now this times this times this. And that was a y. Now it's a 2 minus y. There's your 2 pi, 2 minus y right there. That's your front. That's your thickness. It's all there. You see it? Yes or no? So what's going to change in the C part if we wrap it around the line y equals 5? How much will the radius be? 5 minus y. That's all. See it?
But wait, what about the negative 5/8? How would it?
Well, let's see where that is. Here's y equals negative 5/8. So if this was 1 down here, let's say 1's about right there. So 5/8 would be about right there. So we're going to wrap it around that line right there. What would the radius of this slice be? And it would be 5/8 plus y.
Wouldn't you also have to change the limits of integration from 0? Well,
Nope. Limits of integration are only the collection of slices. And in every case, it is this thing right here that we are spinning. And so we are always collecting slices from 0 to 2. These limits of integration are the range for your slices. Slice, 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 up to the 0 to 2 in every case. It's a good question, though. Y'all see how to finish 34? Any other thing you want to discuss that you've run into so far? Has anybody looked at the quiz review yet? Anyone? No? Well, look at it now because I got this thing all set up and I'm recording it. Because Devin's ready for it. You may not be, but he is. Devin's always ready. Okay, so I'm getting rid of this.
Yeah. Did you guys just work with this?
Do you have any extra copies of those quiz reviews?
Or maybe as well, we're good with that for sure.
Did you lose yours or did you never get one?
We never got one.
Let me come on. It says both of them, so hang on to it after you've taken this quiz. Anybody else need a quiz review? Sorry about that, Devin. That was your commercial break. Anyone else need one? I got one more and I'm hoping to be able to use it myself, but anybody?
No, I'm just kidding. Just kidding.
Okay, so did we pick up everyone? Did everyone come in? 18, 19, 20, 21. Yep. Okay, well, I will remember that. I'm not gonna go to my attendance right now. Okay. So, I'll put this back. Okay, so the quiz review 7-1 to 7-3. Do they have any questions on what they're seeing so far?
First one looks pretty easy.
Anybody wonder about number 7 and what's out to the left of it?
Yes.
Anybody have any interpretation of what you're seeing there?
It's not.
Not multiple choice. Very good. Most people go, what is it? I say, well, if you want to do not equal, you put a slash through it, right? So they're all multiple choice except for number 7. And number 7 is a bonus, and it has to do with surface area. And the formula for that, and a brief explanation, is found on page 405. So if you want to get that bonus, you're going to need to study that a little bit and maybe do a little bit of practice. I think there's some surface area problems in the exercises you might want to practice one or two. So,
I have a question.
yes.
Is displacement where you just take the positive, like displacement can be negative, right?
Displacement is the vector that belongs to distance.
Okay.
Just like speed, or just like velocity is the vector that belongs to speed.
So if we were to do that first one, you would just graph the polynomial there and then move from 0 to 2.
Don't you
Just graph it?
Use the integral
See what
thing
it is at zero.
use.
And then,
Oh, you just integrate it, huh? Yeah.
Yeah.
The integral will give you displacement because the integral takes into account positive and negative values of area, which is distance.
Yeah.
If you want to know total distance, then you would
absolute value.
This is velocity.
in absolute value of the function before integrating it, because that'll take anything that's negative, make it positive, and tell you total distance covered, even if without regard to direction.
Yeah.
So displacement, all it is a concept. Don't make more out of it than it is. Displacement just means where is it compared to where it started. If it started at 5 and it's now at 3, its displacement is -2.
Okay, so pretty much you just integrate the number.
Number one's instructions are the function v of t equals, and I'll tell you this, it's a polynomial. The function v of t is the velocity in meters per second. What are they telling you there? Put units on it, people, pay attention to it. I'll ding you for it this time. I told you enough times, I'm not gonna let you get away with it. Okay, so if it has units in the problem, you better have units in your answer. So this function v of t, which is velocity measured in meters per second of a particle moving along the x-axis where t is measured in seconds. I'll tell you again. Use analytic methods. That means you must show your work if you want credit for this. Choosing the right answer will get you nothing unless you can show me how you arrived at it by hand. When it says analytic or algebraic, that means you got to show me your work. Use analytic methods to find the particle's displacement for, and it will give you a certain number of seconds. So that gives you your from and to for your integral, right? Okay. So once you've designed your integral, because it is a polynomial, I expect to see your antiderivatives done by hand. You can check it with your calculator, but if you give me an integral and then you give me an answer and there's no anti-deriving going on, you will not get any credit for it. You understand what you're up against? Analytic methods with units. Actually, it's multiple choice, so the units are on it. Never mind. And they're all meters. That will not be a delineator between choices. So the first one is multiple choice, so units is not in it, but all the answers are in meters as they should be, so that's displacement measured in meters, okay? Do you all know what you're going to be doing there, or do you need to see an example? By the way, all the answers are in hundreds, and it does say to round to the nearest 10 meters. So if you get 4, what are you going to choose? 300. If you get 217, what are you going to choose?
220.
220?
Yeah.
Okay. Same. Okay. So we're all done with number 1? Number 2. What is the area of the region bounded by? And it gives you 2 curves. Both are polynomials, but both are written x in terms of y. Now, some people come up to me when they're taking this and they say, I don't know which one's which. Show me by drawing in the air what you believe a parabola looks like. Now, show me what you believe a cubed function looks like. Okay, then you should be able to choose. You should be able to tell the difference. One's a parabola, one's a cubed function. You should be able to tell which one's which. Should not have to be able to, I shouldn't have to do that for you. Anyway, it says, what is the area of the region bounded by the parabola? And it gives it to you, and the curve, and it gives it to you. It's a cube function. Round to the nearest whole number. And there are 5 choices. Do you need to see one of those? Both of these are x in terms of y, which means you're going to be integrating along the y-axis.
Can we do
Pardon?
can we do the example you gave us?
Okay, if you'd rather. I mean, that's the only one you've got to practice with. You want me to do it? Number 4?
Yes,
Okay. Example 4 on what?
395.
395. Yeah, this looks quite a bit like it. Look, you got 2 squared functions. No, one's cubed. Yeah, one's cubed. You can see the cube function at the top there. It's on the back end of the parabola, but on the back end of the function, but it is a cubed one. Okay, so if you want to find the area of that blue region, which one are you going to subtract from which one?
Right minus
Right minus left, which means cubed one minus quadratic, right? Okay, and what are you going to integrate from and to in this case?
0, 1.
Okay, what if they had not provided those numbers for you? Or what if the cross point weren't as clear as it is on this, because it's not on the test?
Graph it,
and
run
then
the
run
intersect.
Yeah, now, does that mean you have to solve them both for y first?
No.
Because solving a function for y, if it's a cube function, is nearly impossible, maybe impossible. If there's a cube term and a squared term and a single term and a constant, that's gonna be pretty tough to solve for y in order to graph it. So what are you gonna do?
Graph it the way it is and just replace the y with an x.
That's what I would do.
And then integrate from
And it won't look like the graph on the test. It'll be reflected. It'll be x's and y's switch places, so it'll be up here, and it'll be top minus bottom instead. So now think about that for just a minute with me. If you have that graph right there, and it has been, we switch x and y. I'm hoping I'm going to be able to do this. It's going to be kind of like this. When you switch it around, that's the parabola, and the other one's going to go. Gonna go like this, kind of like that. Okay, so let's say you didn't know these things right here. So you graphed them with a reversal in your x's and y's, so it comes out like this. And let's say, just pretend with me, I drew that graph, but just pretend with me that you found the intersect point of this, and it turned out to be, just pretend, negative 0.52. And this one over here turned out to be 4, negative 1. How are you going to use that to decide how you're going to integrate from and to along the y now that this thing's been upturned? What are you going to use?
the x's.
Yes, you will use the x's for your y's, because this graph that you had to do by reversing x and y, by saying y equals something with an x instead of x equals something with a y, these have now been reversed too. So it is the x values that you will use to integrate from and to along the y. What this graph's going to tell you. Because remember, this graph has all your x's and y's reversed. So if you want to know how you're going to integrate along the y and you reversed x's and y's for this graph, then you can use x's for your y limits on the actual integral. Does that make sense to you? It's a lot of flipping around in your mind a little bit there. Okay? That isn't what happens. If you're going to do this problem, it's very clear they cross at 0 and 1, and that's what you're going to integrate from and to. It's not so clear on the quiz. You have to find your own intersect points, and remember, to graph it, you're switching x and y, so your x's become your limits of integration for y. You okay? All right. So to finish it, to do this one, if we go with the 0 and the 1 on this, it would be, we're integrating along the y, going up from 0 to 1. And it will be right one minus left one, which would be x, or 12y squared minus 12y cubed. Minus the other one, which is 2y squared minus 2y. Now, on this one, remember, you have to show your work. You have to show the antiderivative. Do you want to start antideriving right now?
No.
Me either. I'll clean this thing up. So I'm just going to work on the function for a minute. I'm going to leave the dy off. I'm just working on the function. Okay. The y squares combined, I've got negative y cubed, and I've got 10y squared plus 2y. That's where I want to stop. I'm going to integrate that, right? Do you agree? Okay. What's the antiderivative of that? Yeah, come up here. What's that?
Negative 3y with a function.
Okay. You all understand that and how that was arrived at? Okay, next one,
10/3 y.
and the next one, evaluated from 0 to 1. Now notice that all of these belong to a polynomial, and when you plug 0 in, you get nothing, so, but you should look at that, like I said, if it involves a cosine, you're in trouble. Okay, don't just assume that because that's 0, you don't have to plug something in, but in this case, you don't, because it's polynomial. By the way, if there were a constant on the end, like +5, you want to put that in, because you get a 5 out of that. So always consider this, don't just throw it away. But in this case, you can, because every term's got a y, so every term would be 0 when you plug that in. So all I have to do is plug a 1 in. That gives me -3, because 1's 1 to the 4th, plus 10/3, plus 1. Is that really right? Yeah, that would be 3 1/3, minus 3 is 1/3, plus 1's 4. Would you agree? Is that right?
Yeah.
Oh, good.
Well, I did like a completely different way and I somehow still got the same answer.
Oh.
I'm not entirely sure.
That's right.
I don't even really know how I did it. I anti-derived it differently and
Well, that can't happen. If you got 4/3 and you got a different antiderivative than me, then you're just lucky.
probably.
We got antiderivative. So what I'm saying is you got to get it to here algebraically, and then you got to show me, going from here to here, you don't have to show me how you actually got it, but I want to see the antiderivatives. From there, you can use your calculator to do the arithmetic, but
So this one doesn't say analytically, so.
it doesn't. This is number 2, right?
Does it?
Maybe
Oh,
not.
yeah,
Maybe not.
it
It
does
says,
say that.
it says, what's the area of the region bounded by the parabola and the curve round to the nearest whole number? You're right, it doesn't say that.
See, that was right.
So choose the correct number.
Well, then this is.
Choose the correct value. I wouldn't, Riker, if I were you, I would not anti-derive from here.
Yep, I would be.
Good.
I found
So
out
we
what
find
I
things
did.
a little better.
I pulled out a 2 and then that's why it was.
Wait, could you do that? Like, you could take a 2 and then slap it on the outside.
Yeah, yep. You can factor a 2 out of here and do a 6, a 5, and a 1. Anti-derive those, find the value, multiply it by 2. So I bet you if you did that, you'd get 2/3 here. Multiply it by 2 gives you the 4/3. Whatever you do, show me the integral at least. I need to see at least this. If you get it right, I would like to at least see what you decided to integrate. Number 3, are you ready? Number 3, the instructions are, what is the area of the region enclosed by? And it gives you a couple of curves, and they are trig curves. Again, it doesn't say you have to show your work. It says, what is the area of the region enclosed by? And it gives you 2 curves. They are trigonometric ones, and they give you the interval from here to here. So it should be pretty straightforward. But there's no picture this time, so you don't know what's right and left. You probably want to graph them and see what you can see top to bottom. These are both y in terms of x, and so you'll be slicing this way instead of this way. Okay. Some of the answers are decimals, some of the answers are in terms of pi. You should still be able to choose which one. What did I tell you to practice on? 28? 28 and 29 both involve trig curves and values, so do you need to see any of those?
This is just the same, pretty much.
It is, but I would graph them so you're sure which one dominates the other.
Right.
So you can figure out which one to subtract and which one. And for heaven's sake, people, when you do graph it, design your window so that it goes from and to, and you don't have to look at any portion of it that's not the subject of the problem. You know what I mean?
I do have a question.
Okay.
So for like the example problem was 28.
Yeah.
And the 2 equations that they give, they're both the same thing.
No, sine x and sine 2x are
Oh, I'm
opposite
sorry,
sides.
I read that wrong.
One of them's a horizontal or squeeze, and the other one's a vertical stretch. Okay, all right. So when you go to do 28, you can put y1, 2 sine x, y2, sine 2x. Make sure you're in radian mode, and for heaven's sake, set your window to go from 0 to pi. So you're not looking at any other portion than you need to.
Yeah, but I can't see that.
I don't know. I think it's
So 2 sin x is
Yes, all the way through. Blue dominates it throughout that. Okay, any other questions about number 3? Because I didn't do one for you. Are we good?
What's the answer to 28?
I'm sorry?
What's the answer to 28?
Oh, the answer to 28 is 4.
Man, we get tired.
So I'm not really demonstrating too much for you, but is everybody good on number 3? See what you got to do? Okay. Number 4 is a solid on a base, like those things at the bottom of my cart over there. When you have a base of a certain shape and you're going to put solids on it, stack them up like this, and some dimension of the slices will be determined by the base. Remember seeing those on the? So number 4 on the quiz is like 2A on page 406.
Oh, this thing. I can run through bed on these.
Oh, so that's a lot.
I was like, trying to make that wrong. I was right. Until I was wrong that one time.
There, you get that screaming guy.
Okay, except for, listen. Shh. It's much like 2A. Yeah, it's kind of like that. But on 2A, I think all they want you to do, they actually want you to find the volume on 2A? They just want you to find A? No, you use 2A and actually find the volume. Is that what they said they did? Cross section of the diameter of the XY plane.
Find the formula.
Cross section per
No, it just says find the
the
formula.
solid. I think, okay, it says for numbers 1 and 2, way over there on the left. No, you have to find the volume of the object. So A is a good example to use, but you have to find the volume of the actual object that's described here, and you get no picture either.
Ooh, can we do this one? Got your picture.
All right, but I'm gonna make it up, which means it may not come out very pretty.
I love these games.
That's actually almost better.
Yeah, because then on the test it does.
It's not as hard. Okay, listen to these words. I'm gonna change some of the details. The words on number 4 say something like this. The base of a solid is the region between the line y equals 8 and the parabola y equals 2x squared. The cross sections of the solid that are perpendicular to the x-axis are equilateral triangles. What is the volume of the solid?
Squared.
So, what were the boundaries?
0 to x squared. or something like
No,
that.
wait. Y equals 8 and
Squared.
y equals
2x squared.
2x squared, okay? So we want to have those be between those guys right there, and we're going to have, let's see, it says, the cross sections of the solid are equilateral triangles, and they are perpendicular to the x-axis. Okay, so we better draw this thing. If this is 8 up here, and the parabola 2x squared means it starts here and goes out 1 up 2, out 1 up 6. I'm going to go up 2 a little bit higher. Out 1, up 2, out 1, up 6 would be like this. You graphed it. You can graph it on your calculator too if you want. But this is the parabola we're talking about. And this is the line. And so this is the region. And our slices are perpendicular to the x-axis. It says so in the words. And those slices are equilateral triangles. So this is a slice perpendicular to the x, bounded by this curve and this line. That's my slice. And just so you can visualize it, I hope I can do it for you. There's a base of a triangle right here, and it's coming up like this to where it's equilateral. You see that? So that if I took this slice out and laid it down, it would be this. Now, I will tell you this. These slices on the quiz are not equilateral triangles.
Is it something easier? Like
I'm not going to
square?
say. All I'm saying is I made that part up too. So don't count on the same formula I'm about to use. This distance right here, right there, that distance is this distance. which is 8 minus the curve.
I agree.
And every side is that length. Do you recall? Okay. And do you remember the area of an equilateral triangle? And
B squared root 3 over 4.
S squared root 3 over 4, or A squared, if A is the length of the side. S squared root 3 over 4. That's the area of this where this is S.
How do you remember that?
It's right here in my book.
Okay, so if I would now want to collect all of these from, and by the way, what am I collecting it from and to? What is this right here? 2, and this is? -2. Is it okay if I go from 0 to 2 because of the symmetry and double it? Then this is what I will have, and I want you to think about this before you say, what? I hope you can also, well, I'll do it up here. I think you can, yeah, you can still see the edge of the board. This integral is going to be, if you think about it, now think before you ask me, just think for a minute, it's going to be root 3 over 2 from 0 to 2 of 8 minus 2x squared dx. Nope. Squared.
Is it because it's only half of it?
This is a constant. This piece of my formula is a constant, and I wish to double that. Makes that a 2.
Oh, that's why.
Yeah.
Because we're only taking half of it, but we want the other half too.
See, I'm integrating from 0 to 2, which means whatever I get for this volume, I need to double because I'm really going from -2 to 2, but there's symmetry involved. So I'm going from here to here, okay? Which means it's 2 times this, and this has a constant piece to it. And 2 times that constant piece is root 3 over 2.
It's from 0
We're just integrating one half of it.
But why not the whole thing?
You
Because
could.
that's the way we did it. So you can show us this.
I'll tell you why. Because when I antiderive this, it's going to have x's in it, and I won't have to plug this in.
Well, do we have to find it analytically again?
You can go from -2 to 2. That's fine. Make this root 3 over 4 in that case. That's fine. It's just that you'll have a 2 to plug into the antiderivative and a -2 to plug in, and you'll have to subtract the 2. With my method, I've got the doubling right here, and I only have to integrate from 0 to 2 because I anticipate this antiderivative to have x's in each term, which means I don't have to plug that in.
Do we have to find this one analytically?
So you can get it to here. The setup is what's important. The integral really isn't that big a deal, especially if it's a polynomial. I'm not really interested in your skills with that. It's setting the thing up. So you've either got to go root 3 over 4 from -2 to 2, or you got to go root 3 over 2 because that's twice as big out here. That's doubling it from 0 to 2 of this. This is just easier if you're doing it analytically. If you're not doing it analytically and you're doing it with your calculator, from -2 to 2, it makes no difference. Calculator handles it beautifully. Either way, just account for everything. And this thing, I don't know what it turns out to be. Oh, I gotta square that out and antiderive. That would be gross. I would rather grab my calculator at this point. But that square right there is the same as this square right here, because S is this long. Y'all clear?
So is the problem written like Leah's on the book?
I got 59.
Yeah, that's what I guess.
Just like how
As long as it's not
Yeah,
a
except
square.
you won't have 2 vertical lines that it's in between. It is going to say, it'll have a horizontal line and it'll have a parabola of some kind. I will tell you that. It's gonna be like this.
Looks like it makes between two.
Wait, what are the other?
Two involves the parabola, 3 involves words that are a description. You won't get a picture with this.
What are the different shapes you can have?
Sorry?
What are all the different shapes you can do?
Well, could be equilateral triangle, a square line on tipped up so that it's the diagonal. Could be a circle. Could be a half circle.
Can you confirm or deny that it is not the one?
I'm not going to confirm or deny nothing.
No.
I hate the tips.
It will be a geometric shape for which you know the area.
Could it be a right triangle?
Really?
It might be right triangles, and a right triangle's area is base times height cut in half, where the base and height are the perpendicular legs.
possible that it's a parabola?
I won't get that crazy on you. But, I mean, that's a reasonable problem, but I will not do it to you
I
on
was
a quiz.
hoping for something good.
It'll be something very familiar geometrically to
They're cool.
you, where I don't consider this necessarily familiar, so it'll be more familiar than this.
Don't you have like an intro?
I don't know, but I.
Okay. Any more discussion on number 4? Anybody?
I hope it's circle or
If it was
I feel like you're gonna do
the cross, the pyramid thingies,
No.
the,
No,
The square on its diagonal.
that was the right word.
Diagonal.
Square.
Rhombus.
So that one makes it like what? It involves a root too.
Yeah, you guys kill me. You're as bad as my little Allie. She's only 4 years old. You ask her what this is, she says it's a square. You ask her what this is, just turn it on its side 90 degrees, and she says, no, that's a diamond. No, it's a square.
Rhombus.
Straight.
We call that a diamond. We say a baseball diamond, but it isn't. It's a baseball square. It's more fun to say diamond.
Please tell me it's not that.
Oh, the name of my car is white. And the name of my Jeep, which is red, is heart. So we're taking heart or diamond? You're such a girl. Okay, all right, anyway. Have we discussed number 4 is multiple choice? Are we good with it? Okay. All right, here we go. Number 5. Number 5 is like unto number 4, except you're going to take a region bounded by certain curves and revolve it around something. So it will either be the disc or washer method, depending on whether there's a hole in it or not.
It's.
Just don't forget that it's r squared minus r squared, not r minus r squared.
Wait, can we do one of these?
There's a difference. It's huge.
Maybe both of it.
Do you need to see one like number 5?
Yeah,
Totally.
No, brother. What's the reference?
29
Yep. 49.
59. Same section.
This is the one where we were all like.
Okay, here we go. Let's take a look at 29, the A part. I'll go ahead. You want me to go ahead and do that one? You want me to do one like it so you have something to practice?
Like,
One like it? Say so. I'll do one like number 29A.
either this or.
Okay, so let's read 29A slowly together so we can get some sort of drawing, because you get no drawing with this one either. It says, in exercises 29 to 32, find the volume of the solid described. Find the volume of a solid generated by revolving the region bounded by y equals red x and the lines y equals 2 and x equals 0 about the x-axis. This won't be very hard.
No, this is the one that was just.
What does y equal the square root of x look like? You have an idea? Show me in the air. Yep, okay, good. So it's gonna look like this, and it's going to be the line x equals 0, which is this one. Thank goodness, because there's nothing past it that way. So that's one of the lines, and the other one is y equals what, 2? Up 1, out 1, up 1, out 3. So this would be 2. This is 2, and this would be 4, I think, right?
Sure, why not?
Okay, and it's bounded by this line, and this curve, which is in here.
Yeah, I see that now.
It's gonna be a washer method.
Okay, and so we are going to spin it around the x-axis, which is here, which means we're going to take this region and spin it. And when we're done spinning it, if you look at the bottom of it, it's going to look like a cylinder, right? You look at the inside of it, it's going to look like a parabolic swoop. And it's going to be pointy on the top edges of it, parabola going in, like a wine cup fits in there. Y'all see it? Okay. So would you like to take your slices like this or like this?
Like the first one.
Like this, because it's y equals root x. Yeah, that's a good idea. It's a good indication. So here's a slice of our solid, but here's a slice of our revolved washer. Well, actually, that's only half a slice. It's going to come out here like this, and then have the solid part be right there, so that if I pulled that entire thing out, it would look like a washer that is dx thick. And the radius of this one will be from here to here, right? Radius of the hole, which is red X. And the other radius is going to be from here to here, which is 2. This is big R. That's what I call big R. This is little r.
So 4 minus x.
So what are we going to integrate?
0 to 4.
0 to 4, because that's how our slices are going to go from here out to here. And it's going to be this area that we collect that is this thick. What is that area?
4 minus x dx.
It's r squared, first of all, in general. It's r squared minus r squared times pi, right?
Oh, yeah.
Yes.
Which is pi times 4 minus x. That's a very happy thing. Don't forget your pi, dx. Turns out pretty nice. You could do that one by hand easily. It does not require you to, but you could. Pretty easily.
I don't know how to do, what's the cylinder? Just what's that equation?
The volume of the cylinder?
Like, let's say, like, it was not the wash method,
The
the
disc method?
disc method, yeah.
Pi r squared.
Just pi r squared.
Radius of the disc would be determined by a function.
And that's only if there's not a gap.
Yeah.
Like, it has to be on the x-axis. the whole
Right.
time,
If we were going to rotate this thing instead, just this, and forget this up here, if we were going to rotate just this piece around the x, there would be no holes in your discs. And each one would just be a circle that's area is pi r squared.
You just apply the squares.
2 squared is 4, and root x squared is just x.
You all right, Boston?
Yep.
Everybody okay on this one? Do you want me to put the step that's intermediate to this to show you the squaring? Anybody need to see that? No?
Huh?
Do you want me to put the intermediate step in between here that shows the things that I squared to get this? No?
Good.
Boston, you're good though, right? That was your question, yeah. Okay.
That was smart. Don't get it.
Okay, ready to move on? Okay, the next problem has to do with Hooke's law and the amount of work done stretching a spring.
No.
We say it was 0.
People get this wrong all the time. And my clue and thing to you to remember is, if you're not doing calculus, you're doing it wrong. Okay? Hooke's law is about force. Work, which is what you're supposed to answer, is a collection, it's what this guy does, of forces. It's an accumulator. That's one of the purposes of an integral. It accumulates things. So, to do one like number 6, these are easy to make up, so I'll make one up. It says a certain spring obeys Hooke's law. You have to know what Hooke's law is, by the way. It's pretty easy to memorize. It's just a direct variation. Hooke's law says this: force is equal to some constant times the distance, which he calls x, that the spring is stretched. This is distance. This is force. And every spring has a different constant depending how stiff it is. So if you know Hooke's law and you know what these things represent, then this is how the words are going to be phrased. It says, a certain spring obeys Hooke's law and requires a force of 18 newtons to stretch it 10 centimeters beyond its natural length. 18 newtons is force. 10 centimeters below its natural length. And you might think, well, you're not doing calculus, Miss Jane. I'm just trying to find K. I'm just trying to find K. And that's algebraic. K is 9/5. And so Hooke's law for this spring is force equals 9/5 K. Yes, I do. That is what I mean. Thank you. Where x is a distance. So this is what we've done so far from the words. It says, a certain spring obeys Hooke's law and requires a force of 18 newtons to stretch it 10 centimeters beyond its natural length. That information gets you to here. The question asked, how much work would be needed to stretch the spring 15 centimeters beyond its natural length? People that don't have a clue what they're doing, put 15 right here, take it times 9/5 and call it done. That is totally incorrect. First of all, that would answer a force question. This is how much work. Work is a collection of forces. Now, we need an integral to collect or accumulate a bunch of forces. These are the forces here. They're little teeny tiny forces. Every time you stretch the spring a little bit more, it takes a little more force than the last one. Stretch a little more, take a little more force than the one before that. This will an integral will accumulate them all. It's magical. But if you're not doing an integral, you're doing this wrong. So what do we integrate? Remember, the question said how much work is done in stretching it 15 centimeters beyond its natural length. How much work is done? Work is a collection of forces, and a collection of things is an integral. What do we integrate from and to? 0 to 15. And what are we integrating? 9/5 x. We're collecting the forces.
That's it.
Yeah. So if I were to raise that up, that would be what, 9/10 x squared? That sound right?
Yes.
From 0 to 15. Again, plugging in 0 is no good. So that'd be 225 divided by 10. It'd be 22.5 times 9, whatever that is. Let's see, times 10 would be 225 minus. What is this? I don't want to do the arithmetic.
Yeah.
What? 202.5 what? What's not newtons? Not joules.
Watts.
Because it's centimeters. It would only be joules if I were stretching this thing meters. This thing's unit is a newton centimeter. Just like a foot pound. Newton centimeter. Had this been measured in meters, then you could either call it a newton meter or you could call it a joule. But a newton centimeter is not joule. So you call it a newton centimeter, that would be fine. You don't have to convert this to joules or anything like that. Don't try doing it. Okay? And by the way, there are, this one's multiple choice, and one or two of the choices, well, one of them will be if you just plug in 15 right here. So be careful. Don't do it wrong. How about number 7, which is bonus? I gave you one to practice on that, right? Oh, I just gave you the formula on page 405. Let's see if we can find some that you could practice if you wanted to do the bonus. Is there any surface area problems in this section?
Yeah.
Okay, 55 to 62 are surface area problems. If you want to practice a couple of those, it'd be a good idea. They will all turn out to be irrational decimals. So you want to use your calculator once you get set up. But you're going to want to use the surface area formula and get committed to memory if you expect to get any bonus points on that. Okay, so page 409, 55 to 62, if you want to practice some surface area stuff, the formula is on page 405 in the exploration. Okay, there's your review. See ya.
Yeah.